Hello and welcome to another recording. I'm going to focus this one on, as you see, scientific notation. Again, this is something that often is confusing to students, and I find mistakes get made with it, and mistakes that cost people points on exams, and it just generally can be confusing. So I thought we'd spend 15, 20 minutes going through scientific notation. And you see here my first question, I think is the most critical one that a lot of people simply don't really think about, which is why do we use it in the first place? And the answer to why we use it in the first place is simply because it is really convenient. It doesn't look like the word convenient, but trust me, I tried to spell the word convenient and my dot cam doesn't seem to want to focus right now. So my apologies for that. I'll move it a little bit closer, see if that helps. But it really is a matter of convenience, and I hope to express that to you over the course of this video. So if I were to ask you how large is the hard drive on the computer that you're using, and let's say you might know that your hard drive is 5 terabytes, which isn't an unreasonable number these days, maybe a little on the large side. But you could say to me 5 terabytes, and I would know what you're talking about. Or you could say the following. You could say it is 5,000,000,000,000,000,000 bytes. And if we were having a conversation over the phone where you weren't actually looking at what I just wrote down, but I said 5,000,000,000,000,000,000,000 bytes, you would say, wait, hold on a second. How many zeros? And you would say 0,000,000,000,000,000,000 bytes. And we wouldn't be communicating. But in fact, that is 5 terabytes. And we're simply going to denote that with a capital T. So this is equivalent to that. Which would you rather write? If your career had you dealing with terabyte operations or terabyte hard drives all day long, and you had to put out memos to people in your field or to your employees, and you kept having to write 0,000,000,000,000,000,000 all day long, wouldn't you say, gosh, there has to be a simpler way. Why can't we develop a little code? And we have. And it's called the scientific notation and the prefixes that we all agree to use. So really, this is a matter of convenience, much like a lot of what I've been trying to express to you, like writing reciprocal or negative exponents, just so that we can type them more easily. So tera really represents 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros, or as you probably are maybe screaming into the computer, why not just write this 5 times 10 to the 12 bytes, which is another way to write that. So now here, notice this is that times 10 to the 12 stands in for all of these zeros. It says because the exponent is positive, we would shift 12 decimal places over to get to the 5. So that times 10 to the positive 12 is just replacing all of those zeros. So that this seems 5 times 10 to the 12 bytes seems easier than writing this. But we can write this even more simply by, I like to think of this as like a surgeon, and we're going to excise that times 10 to the 12th. We're just going to, I wish you could see my hands, we're going to pull it out like we're playing Operation in the game, and we're going to, take out the spare ribs. And then we're going to put in the thing that stands for it, the capital T. So if I show this to you, you know that it really means that, and that this really means all of that. So it's a shorthand, it's a code. And we all just agree as to what the code is going to be. So another way of saying this, tera is the equivalent to trillion. Right now, the federal deficit, I looked it up, according to one website, stands at $26 trillion. So, that doesn't seem so bad until you say, well, that's 26,000,000,000,000,000,000,000,000. And then really, if you like commas, you could do that. Or you could say 26 tera dollars, if we wanted to express it with the prefixes. So there are other big exponents. So notice this is a big number, right? Tera is trillion, and giga is billion, and mega is million. Million is 10 to the 6th, billion is 10 to the 9th, and trillion is 10 to the 12th. Okay. So you notice here too that we're going by units of 10 to the 3rd. Well, what is 10 to the 3rd? 10 to the 3rd represents 10 times 10 times 10. 10 times 10 is 100, times another 10 is 1,000. So each one of these steps is 1,000 times bigger than the last step. Okay. So if you had $1 billion versus $1 trillion, the person with the $1 trillion has 1,000 times more money. Think about that. So if you have a 5 gigabyte hard drive versus a 5 terabyte hard drive, the 5 terabyte hard drive has 1,000 times more memory or more bytes. So these are big numbers. We tend not to deal with big numbers in chemistry unless you're really dealing with chemical engineering, where you're moving massive amounts of material around. In the laboratory, we tend to go in the opposite direction. We tend toward smaller numbers. So we could express small numbers in a similar way with a similar code. For instance, I might write that number. And very quickly here, just a little refresher on significant figures. How many significant figures does that number have? Commit to an answer. Write it down next to that number in whatever you're writing these things down in, or if you haven't been writing stuff down, write this answer down somewhere. Commit. This has 3 significant figures. The leading zeros are insignificant or not significant because they're simply telling us the magnitude or the relative magnitude, the decimal place of where the first non-zero digit is. And then we count everything to the right, including trailing zeros. So here we would have 1, 2, 3 significant digits. Okay. Now, we could, I will grant, express this number. We can count 1, 2, 3, 4, 5, 6, 7 decimal places over. We could express this as 7.5 times 10 to the negative 7. And I should have put units on this. Let's say this is a meter. This is a distance that we're measuring. We could express this as 7.5 times 10 to the negative 7 meters. Now, more commonly, though, like up here where we had 6, 9, 12, we tend to get these onto a -3, -6, -9, -12, that kind of 1,000-fold scale. So if we went a few more over, we'd have an 8 and 9, and now we'd have 750 times 10 to the negative 9 meters. Okay, so we could simply express this number as 750 times 10 to the negative 9. Now, imagine you're sitting in an audience listening to a scientific talk, or even just in class, and I say 750 times 10 to the minus 9 meters. Could you write that down? I think you could without me having to repeat it. Now, if I said 0.000000750, would you be able to write that down immediately? Or would you have to lean over to the person next to you and say, was that 0.00000000750, or was it just 0.000000750? How many zeros were there? And eventually you'd have to raise your hand and say, how many zeros? And I would have to say that there were 6 zeros, followed by 750. So by saying 750 times 10 to the minus 9 meters, we are simply communicating better. It is more convenient. So maybe not only just why do we use it, but we communicate much more clearly by using scientific notation. Okay. Now we could do one more thing, just like we said, tera stands in for 10 to the minus, or 10 to the positive 12. We have a prefix that stands in for 10 to the minus 9. And the word that we use, like tera, in this case is nano. Nano is one of the easier ones to remember because nano and 9. So if you just remember 10 to the minus 9 is nano. And then we could express this as 750 nanometers. And notice what we've done again. We've excised the 10 to the minus 9. We've removed it, but we can't just jettison it. Otherwise, we'd end up with 750 meters. We've got to insert the N that stands for nano. Okay. So I think it's easiest if we're sitting in class and I say 750 nanometers. And you write down 750 nm. Look at how nice and compact and condensed that expression is relative to that. And not only is it more efficient in terms of writing, but it's also clearer in terms of communicating. So, win-win. All right. So we now have here a situation where we recognize that nano, anytime we see that N, really stands for 10 to the minus 9. So it works both ways. If we see the N, we can then also incorporate the times 10 to the minus 9. So if I say something is 27 nanograms, you could really rewrite this as 27. Now we're going to put in times 10 to the minus 12, times 10 to the minus 9 nanograms. 27 times 10 to the minus 9 grams. Okay, so notice here I removed the N and stuck in times 10 to the minus 9. This maneuver is going to be very helpful for solving problems, and I really encourage you to use it. You might be in the habit of just trying to swing decimals or enter them into your calculator by looking at a milli and trying to say, oh, I'm going to just swing the decimal 3 places and hope I'm right. This is foolproof. Now I can enter 27 times 10 to the minus 9 into my calculator and know that I'm going to get a problem right with it. So let's look at some operations and things like that. Moving on, we could do calculations. We could say 5,280 kilometers. What I did is I looked up the distance between Victoria, British Columbia, which is on the Pacific coast of Canada, and Halifax, Nova Scotia, which is on the Atlantic coast, so pretty much transcontinental across Canada. I deliberately chose Canada because I know that they post their signs in terms of kilometers. So that distance is 5,280 kilometers. That might not mean much to us in terms of trying to convert that to miles in our head, but I did notice that on Google Maps, it would take about 60 hours to drive that. It's essentially like driving from Seattle to Portland, Maine, let's say, a far eastern point in Maine. Okay, so notice this is 5,280 kilometers. Now we could ask, what if we want that in meters? How many meters would that be? Well, now we can use some of the conversions that we know, right? And kilo is 1,000, right? I have an association of kilo with drugs, right? So a kilo of cocaine, right? Well, you wouldn't be talking about 0.0001 grams, right? The FBI doesn't brag about a big drug bust with small quantities of drugs. So a kilo must be at least 1,000 grams, right? So we can associate these things with things that we know about. So there are 1,000 meters in a kilometer. Think about that. A lot of times people just try to guess at these things. And we simply just have to take our time and say, which is going to have more in the other quantity? Would there be 1,000 meters, thinking again that a meter is about 3 feet, in a kilometer? Or would there be 1,000 kilometers in a meter? Well, think about how big a meter is and think about how big a kilometer is. Well, clearly there's 1,000 meters in a kilometer. Now, if you do this multiplication, the kilometers would cancel. We've seen unit cancellation in previous videos. Unit cancellation is also emphasized in chapter 1. So if you did some of the videos where I encouraged you to read all of chapter 1 in little bite-sized pieces and work the problems at the back of the chapter and the problems that are embedded internally in the chapter, you should be familiar with this kind of cancellation now. And here we'd get 5, 2, 8, 0, 0, 0, 0. So those three zeros add to essentially the end of that number. And now we're talking about 5,280,000 meters. So here again, we just notice the convenience. Is it easier to say 5,280 kilometers or 5,280,000 meters? I hope you agree with me that it's a little bit more familiar and a little bit easier to think about 5,280 kilometers than 5 million meters, 5 million essentially yards. So we use it simply, we use scientific notation, not to be a pain, not to design problems that people get wrong. We use it to communicate better. So just like I think I mentioned on another previous video, I'm learning Estonian. I've got to learn how to communicate. Learning the prefixes is simply learning the language of math and science. That's all it is. You're getting into the culture by learning how to communicate with these things. So very quickly then, we'll go through the ones that are generally of importance to us in chemistry. Some of these are hopefully familiar. Deci is 1/10 of something, right? It doesn't have to be a meter. It could be a tenth of a gram would be a decigram. We don't often use deci too much, but it could be, you know, a tenth of a meter, a gram. We can measure time, so a tenth of a second could be put into deci kinds of units. Centi, again, we have this association of cent with 100, so 1/100th of a dollar would be a cent. Or notice now we could write this as 1/10 squared. If I don't like 1/10 squared, if I wanted to express this as a written on a single line, notice this would be 10 to the minus 2. So all of these are equivalent. I guarantee that if you take out your calculator and do 1 divided by 100, or 1 divided by 10 squared, or 10 to the minus 2, and you turn them all into decimals, you're going to get 0.001. I'm sorry, 0.01. So here we could say a centimeter, right? And you've seen this already. Centimeter would be expressed as cm. And we talked about what a cubic centimeter was. And we know what a centimeter looks like. I'll just put a ruler back up here. From the 0 to the 1, 0 to the 1 is a centimeter. And we said before that 2.54 centimeters is equal to an inch. So if I flip this over, here's 1 inch. And if we come down here, 1 centimeter, 2 centimeters, and a half a centimeter, and a little bit more, 2.54 centimeters to an inch. So that's centimeter. If I were to draw a centimeter now, that's 1 centimeter. If I had 100 of these lined up, another one and 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 another one, and we had 100, what would we have? Well, just like if we have 100 cents, we have $1. 100 centimeters is 1 meter. If we divide both sides by 100, we get 100 cancels. 1 centimeter is equal to 1/100 meters, which is exactly what we said over here. So that's deci, centi. Milli is 1 over 1,000, or 1 over 10 cubed, or 10 to the minus third. So here again, I'm going to focus eventually on these times 10 to the minus 2, 10 to the minus 3. We're going to start going by factors of 1,000 here pretty quickly. And we're going to make that substitution a lot. A millimeter or a millisecond or a milligram is 10 to the minus 3 meters, 10 to the minus 3 seconds, or 1,000th of a second. Take a second in your mind, divide it into 1,000 even parts, and that is a millisecond. Pretty fast. Divide a meter into 1,000 parts. So picture 3 feet. Literally, take time. With your hands, imagine what 3 feet is. If you're about 5 feet tall, imagine what 3/5 of you looks like. That's about a meter. Divide that into 1,000 parts in your mind. That's a millimeter, right? Or look at a ruler that has millimeters. There are 10 millimeters in a centimeter. Notice these are off by a factor of 10. If we were to take a centimeter, if we took this centimeter, so I'm going to circle that, if we took that centimeter and divided it into 10 equal parts, that's a millimeter. Now, if we had 1,000 of these little parts and put them together, we'd get a meter. So that's milli. We'll pick up the pace here. Micro is 1 over a million, or 1 over 10 to the 6th, or 10 to the minus 6. Okay. We use the symbol mu. This is not a U. This is the Greek symbol mu. So it's a fancy looking U for micro. So if we talk about micrograms or microseconds, we'd be talking about 10 to the minus 6 seconds, or 10 to the minus 6 grams, or 10 to the minus 6 meters, a millionth of a meter. Take a meter, divide it into a million parts in your mind. Nano is 1 over that. That's a million. This is a billion. So this is equal to 1 over 10 to the 9th, or 10 to the minus 9. Nano, again, is easy to remember because nano and 10 to the minus 9 go together. And then we have pico. You might be seeing the progression here, 10 to the minus 6, 10 to the minus 9. Logic is going to say if pico is next, we get 10 to the minus 12. So this is part of that pattern recognition that I talked about in a previous video. So this would be 1 over, we add another 3 zeros. So 1 over a million, billion, trillion. This is 1 over 10 to the 12th, or 10 to the minus 12 is pico. You will be expected to know these. So micro, nano, pico. And then the next one is femto. Femto, F-E-M-T-O. 1 over 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 3 more zeros. 1 over 10 to the, use your pattern recognition. What goes there then? 2, 1 over 10 to the 15th, or 10 to the negative 15th. Femto, 15, also easy to remember. The alliteration, nano, 9, femto, 15. So use things that help you remember rather than having to memorize. There are a couple more, in fact. Atto, 10 to the minus 18 grams. This would be 0.0000000000000369912. 001 would be an attogram. 3, 6, 9, 12, 15. No, it wouldn't. One more. And now you see the problem with using the zeros, right? I can get this right all day long, 10 to the minus 18 grams. I screwed this up. 3, 6, 9, 12, 15, 16, 17, 18. This would be the way to express 1 attogram. which would you rather your textbook use? Think about how much territory that would use up. You would pay for each one of those figures because it would make the textbook longer. So do you want your textbook author to use that, or your textbook typesetter to use that, or this? So it's convenient and it's clearer. You are much less likely to make a mistake writing that down. And as I illustrated, much more likely to make a mistake writing that down. So there is one more. Well, there's actually two more. Zepto is 10 to the minus 21. And I'm actually blanking on 10 to the minus 24, but I know it's in the textbook somewhere. Zepto, Yocto, Y-O-C-T-O is 10 to the minus 24. Okay, so going back to then communication, if I write 26 times 10 to the minus 12 meters, that would be, because it's negative, we start thinking about moving to the right because it's going to be a small number. And here this tells us that we have to move 12 decimal places to hit that 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would be 0, 2, 6. Well, it would be 26 times 10 to the minus 12. But again, we probably don't like having to write that. So we might not even like writing this 10 to the minus 12. Go back to that previous page. What was the prefix for 10 to the minus 12? It's not nano because we know nano is 9. It's not femto because we know femto is 15. So it's either going to be pico or micro. You'll use micro a lot, 10 to the minus 6, especially in like biochemistry. This is pico. So we could rewrite this as 26 picometers. So if you're typing a textbook, this is way easier. And if you're trying to understand math, this is way easier than that. If you have to do a problem with picometers though, so let's say I wanted you to convert 26 picometers to kilometers, let's say. I don't know the conversion directly between picometers and kilometers, but I do know the conversion between pico and meters to kilometers. So let's do that. 26 times 10 to the 12th. Well, we could do it two ways. We could do 26 picometers, saying 1 picometer is 1 times 10 to the minus 12th meters. So again, we have to think about how small a picometer is. And then there are 1,000 meters in a kilometer. So we would take 26 times 10 to the minus 12, divide by 1,000, and we would get 26 times 10 to the minus 15 kilometers. Now notice I was able to do that in my head because this is 10 to the 12th divided by 10 to the 3rd. This will be the last thing we do on this video before we pick up a few more examples on the next video. 10 to the minus 12 divided by 10 to the 3rd. Oh, I don't know how to do that. Well, think about what we did with exponents. If I asked you to solve this for exponents, you would say, okay, when I divide, what do? I subtract. So I would have minus 12 minus 3. Well, what is minus 12 minus 3? It's minus 15. So this would equal x to the minus 15. We do the same thing with scientific notation. 10 to the minus 12 divided by 10 to the 3rd would be 10 to the minus 12 minus 3, which is 10 to the minus 15. It's really why we like scientific notation, because we're always just dealing with 12, 15, 9. Makes it pretty convenient. Notice, however, though, in order to do that, I'm leaving this as 26. I'm not writing this as 2.6 times 10 to the minus 14, right? Which would be legitimate. We could rewrite that number as 2.6 times 10 to the minus 14, but we tend to want to leave things. I understand the number 26. I understand the number 10 to the minus 15. I understand 26 times 10 to the minus 12 as well. So we tend to operate where we leave these things in convenient orders of three orders of magnitude, I should say. Okay. So I'm going to close this video on scientific notation, and the next one that we do will reinforce some ideas about how to work with them as units when we have, let's say, megabytes and microseconds combined in the same problem. So again, I hope you found this useful. Tune into the next video where we pick this topic up again.